this the first? Anyway, so this talk is not about lean, it's more about formalization of Periodical functions in lean. Lean is a computer language, and I'll tell you more about it ahead. Um, so first, I'm pretty sure, there we go. Yeah, so I'll speak about Piadic measure theory in lean. And first, I'll give you a brief introduction to lean, then the math part of what I'm doing, then how I implemented the math in lean, and finally, what I plan to do in the future. Okay, so what is lean? It's an interactive theorem prover. Basically, lean is used to verify that theorems are correct. It sounds a bit weird, but the point of it is that if you want to make sure that what you're saying is 100% accurate, then you feed it to the computer, you feed the theorem and its proof, and then the computer will tell you if there are any errors in your proof. And I'll give you an example, a live example of it in a while. I should also mention that this is a Microsoft product developed by Leonardo de Mora. I think we are supposed to mention that every time we speak about lean. So, okay. And now there is a very big growing community, especially in US. There's a very big community of mathematicians using this. Lean is a computer program, but it also has a mathematical library, which is called MATLAB. And what people are trying to do is they're trying to put in these theorems and the proofs of these theorems and just store them in this MATLAB so that you can use them, and right now some very big things are going on. For example, Peter Schulz's liquid tensor experiment, perfectoid spaces, that has been put in and verified. Then I don't know, the sphere reversion project, if anyone is familiar with that. You take a sphere and you try to turn it inside out without any folds or creases. And that is something very difficult, right? Because a lot of it's a differential geometry thing, and a lot of that is based on drawings. How do you explain that to a computer? So it's a pretty big project and should be done very soon. Okay, so what is the difference? Why is doing math in lean such a big thing? Because lean uses something called type theory instead of set theory. So in math, in math, there are sets which we use as the basis, but in lean, you use something called types. And this makes my life very, very difficult. I will explain why. So what is a type? It's basically like a set, except you can have a particular element belonging to two different sets, but you can't have a single element belonging to two different types. Okay, so for example, let's say 0 or 1 in the naturals. So 1 of type naturals and 1 of type integers are two separate things. They are not the same thing, although in math we might think of them as the same thing. Okay, and there are types for everything. For example, the set of a space is a type. Natural numbers is a type, real numbers, everything's a type. Okay, similarly, there is a type called prop, which is you can say the set of all propositions. And when we speak of an element P of type prop, that means P is a proposition, and an element T of type P would mean that T is actually a proof of P. Okay. And this works for definitions as well. So I could have, let's say I'm defining a function, and then I say that the identity is of type function. So it's a particular function having type function. Okay. And one of the things about lean is that it does not remember the proof of any proposition or lemma. So if you give it two different proofs, that is the same thing for lean, because it's just an element of that type. So say I have an element P of type prop, and this P can have, it's either empty or non-empty. If it's non-empty, means that it has a proof. If it's empty, it means it's false. It does not have a proof. Okay. Finally, how do I identify things of different types? For example, how do I identify one in the integers with one in the naturals? You have to define a map from the naturals to the integers, which we know is inclusion. And then you define one in the integers to be the image of one in the naturals under this map. And I really hate this because it makes my life very difficult. A lot of times I'm working with, a ring and I want to show one is not equal to zero. Then I need to somehow bring it down to the naturals and then show that one is not equal to zero there. So it's not, zero there. It's not the same thing in the ring. But this is what is needed for, complete 100% accuracy and rigor. Yeah, so we know for sure that things work then. Okay, now coming to something called type classes. This is a pretty unique feature of Lean. I should mention there are a lot of different theorem provers. For example, Isabel Hall or Koch. But sorry, but the thing that makes Lean special is there's something called type classes. So a class is like okay, so first you have a definition, then you have a structure where you have a lot of things put in together. So for example, let's say if you want to define the units associated to some ring, then there are actually four components to units, the space of units, which is the unit, its inverse, the map, the function, well, the property that the unit times its inverse is 1, and the property that the inverse times the unit is 1. Okay, so all of these things are classed together, are put together to make something called a structure. And then there's something called a class, which is a specific type of structure, which means that I can basically add properties to this class, which Lean will remember. For example, let's say I'm talking about a monoid. Oh, okay. Let's say I'm talking about a ring of characteristic P. And then I want to say that this ring actually has characteristic P. Then Lean will remember that property if I initially define this ring as a class. And this entire thing is called type class inference system, and it's very useful. Because otherwise things would get very difficult if you had to keep reminding the computer that the integers, for example, are an additive group and stuff like that. Okay, right. So maybe this is a good time for me to show you an example of what I mean. So this is Lean, and what I'm doing over here is importing a basic file called this data.nat.basic has the basic properties of the naturals. Okay, so first let's just check that there is this function nat.stuff, or let's just check the naturals exist. So I said check naturals, or let's see, print naturals. And over here, you can see I'm getting a goal, which tells me that the naturals exist. They are an inductive type. And there are two things that make the naturals: 0 and the successor function, which takes n to n plus 1. And using these two things, you can build all of the natural numbers. Okay, So now let's try to prove this lemma over here. What does this lemma say? It says, first of all, I named it h, then I'm giving it an input n, which is a natural number, and the fact that n is positive, and the fact that n is greater than equal to 1. Then I want to say that n is not equal to 0. Okay. And now I'm going to try to prove this. And here you can see in this goal window that I have this goal n not equal to 0 and all the information is here. So let's try to prove this. First, I'm going to try and give an inductive proof. Also, feel free to stop me or ask me questions at any point. So I'm going to try to induct on n. And you can see that my goal over here has changed. Now I have to prove two things. First is the case where n is equal to 0. So all my arguments over here, n positive and n greater than equal to 1, have been replaced by 0 positive and 0 greater than equal to 1. And the second goal is where n is equal to the successor of some integer d, some natural number d. And successor is just d plus 1. Okay, so how do I do this? Sorry over here is just used to, telling that, okay, I will prove this later at some point, and it will give me this goals accomplished thing, which is the only reason why I do lean, because it's very nice to see this. Anyway, so how can we prove this? I want to show that 0 is not equal to 0. Well, one way to do this is to say that, okay, I have 0 greater than 0. This is false. So this should be false. So first I use something called x falso, which changes my goal to false. Then I'm going to try and show that this implies something false. And what I've imported here has some lemmas already. So let me try to use those. So now I'm defining a lemma, which is called nat.not less than 0. And you can see over here, it says, this lemma says for all a in the natural numbers, a negative is false. Okay. So I'm going to put this, and that gives me that if 0 is negative, then it's false. And now that I have this, this is exactly what I want. So I do an apply hn prime. And that solves this goal. Okay. And similarly, okay. So now I'm trying to say that the successor or d plus 1 is equal to 0 for some natural number d, which again we know is false. And we already have a lemma for that, which is called nat.suck not equal to 0. So I just apply that, and that tells me goals accomplished. Okay, so this is some way to prove this, which I don't believe is very efficient, but it exists. Now, there is a way, there is something which Lean does called the Linter, which basically checks that everything you proved in this file is correct and everything works well. So now here you can see it says checking one declaration, all checks have passed. Let me make some changes, okay? Because I think this is a pretty inefficient proof. So I have another proof that I already typed out, which I'll just put in. And let's see if things change. Also, I want you to notice that right now, one of the good things, advantages of using Lean is that sometimes it can catch when you're having some hypotheses or arguments that are not really needed. For example, I did not use n is greater than equal to 1 at all over here. So let me just change this proof. Sorry, there's a lot of traffic. Okay, so simp is just some tactic which already knows some lemmas and it will just put that in. So my proof still works. And let me change this lemma to a definition. Okay, so now I'm just making a definition for n not equal to 0. Now the linter tells me that this is actually, it should not be a definition, it should be a lemma. It also tells me that this argument h is an unused argument and I can remove it. And that's actually pretty useful. So let me do that. Let me do this. I've removed the argument and now it says all checks have passed. Okay, so this is a pretty trivial example, but this turns out to be a very useful property. People have proved a lot of things and removed a lot of unnecessary assumptions. For example, mostly what is used in Lean is monoids instead of groups, which is monoids are basically not having the, what property do they not have? Associativity. Thank you. So monoids don't have associativity, which groups have. But yeah, so it turns out you don't actually need that property in most cases. And the linter helps with finding these sort of things out. Okay, so that's a very basic example of how Lean works. Anyway, getting back to the math part of what I'm doing. So I've been working on something called Periodical functions and formalizing this into in Lean to make sure that everything I know is correct. And my basic reference for this is Washington's Introduction to Cyclotomic Fields. And it's actually maybe 2 pages over there, but I've spent 2 years on this project now and it is still not complete. So this, because I think a lot of mathematicians end up writing things like this is trivial or this is easy to prove without actually giving a proof. And then it turns out it's non-trivial. So it takes time. Okay. Okay, so I'll just give a definition of Piadic functions. For that, we need to understand what locally constant and continuous functions are. Obviously, I'm sure you all know what continuous functions are. A locally constant function between topological spaces is a function such that the preimage of any set is open. Another definition of this is if you look at any point in the domain, it has a neighborhood over which the function is constant. Okay, and these are equivalent. So for example, you can look at the characteristic function on a Clopen set, and that is locally constant. And I believe this is an if and only if condition. Okay, I'm just going to call the space of locally constant functions LC of xy. And obviously every locally constant function is continuous. Now I'm going to be using X over here will denote a profinite space and A will be a normed ring. And because in this specific setting, the space of continuous functions has an induced subnorm, which we'll be using. Okay. Some further properties of the Piadic integers for those who don't know. ZP has a topological basis of Clopen sets, which comes precisely from the profinite limit. So you look at ZP going to Z mod P bar n Z for every n, and the pre-image of every singleton gives you a Clopen set, and that is exactly this topological basis here. Then we are going to be looking at characteristic functions corresponding to each of this. UNA is basically A plus Z mod P bar n, sorry, A plus P bar n ZP. Okay, so one of the results is that this set of characteristic functions linearly spans the space of locally constant functions. It's not a basis, but it definitely linearly spans. Okay, so basically, if you look at a locally constant function, you can find an n positive such that f is of this form here. And similarly, the same thing holds for a function going from z mod dz to cross zp to our ring A, because z mod dz is a discrete space, so things remain the same. But I guess to extend this to any discrete space, I would need it to have some sort of additive and compatibility property with the Piatic integers, which is why I stuck to z mod dz. Okay, now coming to a Piatic measure. First, we define something called a Piatic distribution, which is an A-linear map. If you have a normed ring, you take an A-linear map from the space of locally constant functions of x to A. And then a measure is just a bounded distribution, namely norm of given any locally constant function f, norm of phi of f must be less than or equal to k times norm of f for some positive constant k. Okay, and one specific example is the Bernoulli measure on the Piadic integers, which is a very famous and very important example as well. So it's defined on the characteristic functions in this way, and then you can linearly extend it to the space of all locally constant functions because these linearly span that space. And yeah, okay, I'll come to the salient underlying points later. So using this, we can define something called a Piadic integral. So you take a locally constant function f, and the integral is just the evaluation with respect to this Piadic measure. And a very well-known result is that the space of locally constant functions is dense in the space of continuous functions. So then you can uniformly extend this integral and continuously as well to get this linear map. And basically this map is you look at, you take a function here, it's the limit point of some locally constant functions. You evaluate those under this mu, and then you look at the limit of those functions. That gives you this point here. Okay. Now, some history on the Periodical functions. We know what the Dirichlet functions look like, given a Dirichlet character chi, which is basically just a multiplicative homomorphism. It's defined in this way, and it's meromorphic with a pole at s equal to 1. Now, you want to extend the same thing to the Piadic spaces. And this is called the Kubota-Leopold Periodical function, where you get a LP of S chi to be a meromorphic function with the pole at s equal to 1. And it basically comes from this extension over here, where this 1 n is basically a positive natural number. And you can extend this to ZP. In fact, you can also extend it to CP, which is the Piadic completion of the complex plane. And this chi is a Dirichlet character, omega is a Teichmüller character. Okay, so sorry, no, this is correct. This is the relation between the Piadic function and the Dirichlet function. Okay, so what was my goal? My goal was to, first of all, put in this definition of the Piadic function. And secondly, this is the property which I wanted to put into name. Why? Because I want to get to a point where I can state Iwasawa theory in U. And to do that, Iwasawa theory, basically, the main conjecture has two sides. The left-hand side is in terms of the Periodical functions, which is an analytic object. And the right-hand side is in terms of the characteristic functions, which is a completely algebraic object. So I wanted to have this in there because it's useful. And what this says is you take a Dirichlet character chi, which has conductor D, P par M, where D and P are two co-prime natural numbers and P is a prime number. Then given an S in ZP and natural number C, co-prime to both D and P, this integral, which is the Piatic integral with respect to the Bernoulli measure, is some constant times LP of minus S chi. Okay, and one small thing to notice over here, the integral is actually over the units of Z mod dz times Zp, not over Z mod dz times Zp. Okay, so I'm almost there, which is what I've been saying for 6 months now, but I really do believe I'm almost there to prove this. There are a few problems with this because the definition that I showed you for meromorphic continuation was challenging to formalize at that specific point because first of all CP did not exist in the it still does not, and secondly meromorphic continuation is something that's not easy to work with. So instead, what I did was I chose this to be an alternate definition for the Piadic function. And so to do that, I would have to define Piadic distributions, Piadic measures, the Bernoulli measure, to show that the Bernoulli measure is a measure, and then to be able to write down this integral over here. So okay, so what's the point? I mean, if I make this definition, then I do need to show that it satisfies the properties of the Piadic function. Namely, sorry, I did not mention it here, but basically the Piadic function has takes special values in terms of Bernoulli, generalized Bernoulli numbers at negative integers. And so I would have to prove LP of 1 minus n pi is something in terms of Bernoulli numbers. Okay. And that's the theorem which is not done yet. This is in lean. It took, I think, around 2,000 to 3,000 lines to prove, but sorry, to define, but it's there. Okay. Now, just a bit about implementation. Actually, maybe I can tell you a bit about implementation. Okay, so these are basically some of the challenges that I faced while formalizing this stuff. So first of all, this C XY or C alpha beta already existed in Lean, and it already had an existing topology on it. But it was not the topology that I wanted, which was the topology induced from the supremum norm. So then I had to show the equivalence between the two, which is, it's fine, but it's an additional thing which takes time. And in fact, the topology over here was the one that exists on bounded continuous functions, which is a little different. Okay. Secondly, the second thing that took time was that to show that the Piadic integers have a topological basis of Klopen sets. Now, one thing that is very important in Lean, in MATLAB, is that the maintainers of the library will not allow you to put in any theorem into the library unless they are completely sure that it is the most general thing possible. So I can't put this as it is. So what I actually had to put in was that every locally compact Hausdorff totally disconnected space has a topological basis of Klopen sets, which is a bit more work, but it follows a similar proof. And as a consequence of that, I found some small result that every locally compact Hausdorff space is totally disconnected if and only if it is totally separated, which was interesting. Okay. One of the major challenges for me was to deal with the Piadic integers and Z mod P bar and Z. And it's basically because of the coercions that I mentioned to you in the beginning, because everything has different types and to identify them takes a lot of work. So I had to use these maps, val, cast, and 2Z mod pow, which I think val you would not think about as a mathematician. For example, if you were to think of, say, an element A in Z mod NZ, sorry, if you were to think of an element A in Z mod NZ, if you wanted to think of it as a natural number, most mathematicians would forget that there are, well, not forget, but there are several choices for this because A is an equivalence class in Z mod NZ. So what exactly is the right choice to make over here? In this case, the right choice is to take the least element in that class, equivalence class. That's how this map val is defined. Similarly, you have a map cast, which goes from Z mod NZ to any ring R. But this is a ring homomorphism if and only if, maybe not if and only if, but definitely if the characteristic of R divides N. And how it works is you take an element A over here, you take it to the naturals using this map, so val of A, and then val of A is in the ring R naturally, because every natural number is in every ring. So, so there's basically a lot of ways to think of these things, right? If I'm looking at an element in R, I can think of it as coming from Z mod NZ, or I could think of it as coming from the rationals, and these could all be different things, right? So then you need to show that the identification of all these things is the same, which is sometimes non-trivial and sometimes also not always true. So this did take a lot of effort. Okay. And right, so here I'm just giving details of the proof of why these sets form a Clopen basis of ZP. I think it's a lot of details, so I think I'll just skip it. Okay, and finally, this linear continuity of this map was actually a nice thing, because this map over here is dense inducing, which means it has dense range and the topology is induced, so things become nice. In fact, you can give this space over here a very nice algebraic structure, random metric space structure, so things work out very well. Plus, the boundedness of the measure turns out to be equivalent to uniform continuity of the integral. So that was helpful as well. Okay, and right. So showing that the function that I defined, EC, is actually a measure was a little difficult. Sorry. So first of all, to define EC, where is the definition? Right. So over here in this definition, this has to take values in an arbitrary ring R. Okay. C is a natural number. A is a unit in Z mod P bar NZ. So I can't actually do this. C inverse times A makes no sense. What is C inverse? What is, what does inverse mean, first of all? And this actually turned out to be a little problematic. So what I had to do was take C in Z mod D P power 2n, take its inverse over there, and then take its val, take the val of this, and then look at this as an element of Z mod D P power nz, and then take the val of that. Um, and this is just one combination, but there are tons of them. So it took some work to firstly define it, and then to show that it is a measure was a 3-step process. Sorry. Right. So it was defined on the characteristic functions, and to extend it, again, there were several choices. I chose to extend it using this sequence GN, and then define the usual thing, ECFF, to be the limit of GN. Right, and also to do this, to prove that EC is actually bounded, I needed the norm of A to be Archimedean, which is also where I told you about the linter. So the linter was helpful to remove all these extra assumptions that I had on A. It's only here that I started needing A to be an Archimedean norm ring. Okay, and to one of the other salient points to show that this GN is a eventually constant sequence, I needed to use the fact that every locally constant function has corresponds to a discrete quotient. So you relate x and y if and only if f of x is equal to f of y. And you define another quotient to say x is related to y if and only if x is y mod dp power n. So then there is this lemma which says that for every locally constant function f, you can find an n such that x is for all n bigger than that. If x is related to y with respect to fn, then x is related to y with respect to f, which is the same as actually saying that this sequence over here is eventually constant. Yeah, so this was the most general way to attack this problem. But I'm sure easier proofs might exist. Okay, and finally, right, so another challenging thing was to show that, like I told you, I was working with the integral over z mod dz times zp star, as in the units. So I needed to show that the map from the units of zp to zp is continuous. And the problem with that is you need to think about how units of zp is a topological space. And indeed, the way it's defined is you look at this map taking u to u comma u inverse, which is called the embedded product. And you look at the pre-image of this map and use the induced topology, basically. And what I wanted was for the units to have a subspace topology. And this is true that these two topologies coincide only if the group is a topological group, which ZP is. So things worked out well. Okay, so coming back to the definition, I had to tweak some things. Like I told you, first of all, I was using the integral as a definition, the Piadic integral. And another thing, like I told you, CP did not exist in Bean. So what I used was, instead of using S, which comes from CP, I used something called W, an element of the weight space. The weight space is basically all those homomorphisms from Z mod dz times Zp to A, which are also continuous. And I don't know if you remember, but over here there was an A power 1 minus A power S, I believe. So W is basically A power S. And so our domain of the function changes, but essentially it's the same because of some highly non-trivial property of the fact that the weight space corresponding to ZP has a particular form in terms of ZP. Anyway, so another problem I faced was that this is happening. So Washington does this in CP, but I was doing this in a general normed commutative QP algebra. So I didn't have some things. For example, I didn't want R to have division, say. So I can't actually divide by this. This is not always invertible, so I can't always invert this. But it turns out that this is an inconsequential factor. So I just absorb that into the definition. And so the definition is basically just this integral. And finally, I just wanted to say that it turns out you can also define Piadic functions for modular forms in a very similar way, which is being done by, I believe, Maser and someone else in a work from the 1990s, I think. So yes, I think this exact same way can be used to extend this Periodical functions attached to modular forms instead of Dirichlet characters, which is very interesting. Once we have a good enough knowledge base for modular forms in Lean, it should be easy enough to do it with whatever I've currently done. Okay, so like I said, oh yeah, another thing, this definition over here is actually dependent on this number C because I have incorporated it in over here. And this C is just some random number. So I need to then show that this definition is independent of C. But that turns out to be the same as looking at the special values of this L function here, or equivalent. And so if I prove that, I've also proved the independence of C. Once I do that, like I said, I would like to move towards stating Deva-Sava mean conjecture and maybe adding something more to Piatic measure theory. On that note, I would like to say that I found some interesting links between measure theory and some other measures, Piadic measures and some other measures. And all of these links seem to come from knot theory, which is very random, but it works. Okay, and all of my code is available on GitHub in case anyone's interested to have a look. You can always message me. And yeah, this work is completely possible because there's so many mathematicians working in so many different areas. Like I mostly spoke about measure theory and I spoke about topology, not number theory. And these things were developed by topologists and analysts, which is why I could do whatever I've done. So that's something great that this is open source. Nice. That's it. Any questions?
Do you have manifolds also in Lean? Like some way to define?
Actually, I can just show you if we have manifolds. I'm pretty sure we do, although I don't work in that department. Let's see. There you go. Over here, this is our library searching. And
oh,
there's a lot of stuff. So yeah, I'm pretty sure. Let's see. So geometry manifold. Geometry manifold. Yes. So we have something, a lot of things. There's Lie groups. I know one of my supervisor's postdocs has done some big theorems in Lie theory. He's formalized it in Lean and he's given the classification of Lie algebras as well. So.
oh. Interesting. How do I search this without your application?
I can give you the link. There's you can, sorry, give me 1 second. I'll just send it to you in the chat. All of this documentation is done online, so yeah. There. If you go to the left-hand side column, there's something called library. And in library, you'll be able to see algebraic geometry, algebra, topology, geometry, everything.
Nice.
And if you want to see, I can also show you the actual definition of a periodical function. It's very ugly, but I'm very proud of it. There. So this is the definition. You can see it's on line 4080, and it took me 3-4 files before that to get here. So there. It's, I don't know how many lines long, but standard definitions are generally 1 line long.
So these last 3 lines in the comments, is it like asking people to make it better?
I think at this point, no one can read my code. It's pretty unreadable, and that's totally on me. But yeah, if this gets accepted into the mathematical library, I have not attempted that yet, then people could try to make it better.
Okay.
And if you want to have a read through, this says that the GCD of D and P is 1, the fact that M is positive. This is saying that the function from ZP to R is injective, which is not actually needed because R is a QP algebra, so I should not be needing this. And that injection is continuous. The GCD of C and P is 1, the GCD of C and D is 1. This over here is the non-Archimedean condition on the norm. Sorry, the Archimedean condition on the norm. This over here says that the constant I showed you, which I absorbed into the definition, is a unit. But this is an unnecessary hypothesis, which I have not removed, but I really should, because I'm going to be removing this term entirely. And finally, the definition over here is a Piadic integral in terms of the Bernoulli measure. And the function over here is this chi omega inverse. Instead of inverse, I've used power p minus 2 because it's with this. So omega power p is 1 basically times the weight space. Sorry, the element of weight space, which was the a power s. And this over here tells you that this function over here is continuous because I need the integral was defined on the space of continuous functions. So it will not accept an argument of a function which is not continuous.